Welcome to the video presentation of the Eurofins 2023 invited CGF paper, Visual Exploration of Financial Data with Incremental Domain Knowledge. This is a joint work between the CVAST and Distributed Systems Group at TU Vienna and the Complexity Science Hub in Vienna. I am Alessio Arleo from the CVAST Group and I will be your presenter. This is the outline of the presentation. We will start from the motivation, then describe the contribution and design. Finally, I will present the evaluation and discuss the takeaway message and conclusion. There are several types of data that are of interest of the researcher that approaches the visualization of financial information. These are, for example, stocks, fund trends, risk, metrics, and so on. However, the knowledge of monetary flow between firms can give a significant advantage, both in terms of investment planning and research, but also it allows to understand the effects on real economy of policies and regulations. However, these are also quite hard to come by. Throughout our related work research, we found that research in visualization for finance heavily rely on data from industry partners. Design decisions then tend to be based on fragmented data sources. There are several potential sources of information, for example, open data and paid datasets, but also simulated or inferred data from agent-based simulations or by guesstimating the information from other available ground truth. This suggests that there is not a lack of financial data, but rather an abundance of it. The problem is that can be very scattered with different formats and with different level of details. Let's make an example with Austria, a country in the European Union. One example of data source are newspapers that can be very detailed but limited to specific regions. Then we have government open data and paid datasets that can shed more light about individual firms and or local financial contexts. And then there is also domain knowledge, which is mostly not encoded and eventually hard to include into reports or forecasts. However, all this information have in common that they are the effect of the interactions of the individual firms. Therefore, there is a big picture that is missing. What if we could reuse all available financial information from different sources and visualize them into a systematic and organized and homogeneous way? This is exactly what we plan to do with our contribution. We present in this paper Sabrina, a visual analytics approach for multi-scale dynamic financial data exploration. Plus, we integrate a pipeline for the guesstimation of financial transaction networks that can reuse information from newspapers, commercial and freely available databases, and domain knowledge of the users. This is a snapshot of the system. Its main tasks are an overview of the economy on different scales, from local to regional to national, the capability of monitoring changes in different financial metrics over time, investigate relationships between financial and tax entities, and finally inspect and validate transaction models. Let's focus on the design. We follow the approach by Miksch and Aigner, the so-called design triangle. This models the whole design process on three pillars: the data, the users, and the tasks. In our case, we divide the data into micro and macro. Micro data concerns information about individual firms, such as their name, size, and yearly balance sheets. The macro data instead refers to aggregated data about groups, large groups of firms, which can include information about individual productive sectors and how they are related to each other, annual investments on entire regions, and so on. As users, we target policymakers, financial experts, journalists, and statisticians that are not necessarily expert in visualization, but they are in their own application domain, that is finance in this case. We already seen the tasks the design tasks of this system in the previous slides. We model our data as a weighted directed network. The nodes of these networks are the individual task entities, factories, banks, companies, and so on. Each one of them has some specific information, such as the name, the sites, the productive sector, and so on. The edges of this network are the transactions that make up the firm-to-firm network. The weight of each of these edges encodes the transfer entity, the amount of money that is transferred from one entity to the other. This information, though, is dynamic, with one separate instance of the transaction network per each year. Further details about the model generation pipeline can be found in the paper shown in this slide. For completeness, I will now give some basic details. Our approach is founded on the premise that one can merge different financial information sources to incrementally build a fine-grained transaction network. With this information, constraints can be formulated that will drive the generation of the model. These constraints are encoded as first-order formulae within satisfiability modulo theories. These, fed to an SMT solver, will yield different possible solutions, so different transaction networks that by construction satisfy the initial constraints. The more and the better constraints, the more realistic the final instance of the transaction network will be. This operation is now carried out offline. The system, though, can also accept different transaction networks that are generated using different methods. Financial information formulated in natural language, coming, for example, from literature, paid dataset, or domain knowledge, can be translated into mathematical constraints, for example, as follows. This is the main view of the system. Firms are placed on the map based on the coordinates of their headquarters, and they are binned together based on proximity using an hexagonal tessellation or based on the administrative division, such as provinces or regions. The color coding depends on the currently selected financial metric. By hovering on each aggregate, it is possible to see the composition in terms of sector of the firms inside it. Time can be navigated using the timeline, and the colored bar on top of it shows the temporal trend of the currently selected financial metric. From the left bar, it is possible to change several parameters of the visualization. It is possible to change the hexagon radius, the type of aggregation, the currently selected financial metric, and it's possible to filter out firms depending on their sector. Different metrics have been implemented, but there is a support for multiple of them. In this case, and each one of them has their own color encoding. These represent the cash inflow. By clicking on each of the sector on the map, it is possible to access the microdata of all the firms that are binned into the specific area, providing information such as their ID, the sector, the average cash flow, and the number of employees. Financial transaction models are loaded into the system using the Model Selection tab. Models can present different options that can be selected prior to loading the model into the system, and multiple models can be loaded at the same time for comparison reasons. Transactions are represented as curved arcs, and color encodes the direction, from red to green. Color brightness instead encodes the transaction amount. By default, transactions are bundled together to ensure readability and to avoid clutter. With the Transaction tab, it is possible to see the details of each bundle. Bundles can be deactivated to inspect the individual transaction, which can be useful when analyzing small local financial environments. We will now discuss two potential use cases of this system. In the first example, we simulate a shock on the tourism sector in the Vienna region and evaluate also the possible effects on tourism sector in the Vorarlberg region. By filtering out all firms with the exception of the ones belonging to the tourist sector and changing the metrics to the cash inflow, we can immediately see that in the Vienna region there is a much higher financial turnover than in Vorarlberg. This is already a first indication of financial vulnerability. We load a model to understand if there are other possible correlations between the two regions on the tourism sector. It is possible to see that transactions are bundled. So we have one bundle for each of the outgoing transactions from Vienna and one for each of the ingoing transactions to Vienna. It is possible to see from the close-up that the selected transaction arc that goes from Vienna to Vorarlberg is amongst the ones with the lowest value, thus suggesting limited correlation. Therefore, we can conclude that if a shock happens in the firms in the tourism sector of Vienna, there will be a limited impact on the firms belonging to the same sector in the Vorarlberg region. These conclusions, however, depend on the reliability of the model they were derived from, and this brings us to the second scenario, model validation. One way to validate a model is to check whether it contains transactions that are suggested either from ground truth or domain knowledge. In this case, we are testing whether one of our models contains transactions that belong to firms in the automotive sector. Domain knowledge suggests that car parts in Austria are built in the lower parts of the country and assembled in plants in the upper part of the country, specifically in areas with higher density of automotive firms like the ones highlighted in the figure. A valid model should then have transactions between firms in the automotive sectors in these regions. Looking back at one of the figures I showed in one of the previous slides, it is possible to see that one of the loaded models actually has a transaction that is highlighted in the middle of the picture. This, therefore, suggests that this model can be a good base for further refinement of it to make it even more realistic and reliable, and it can be used later then for decision support. We now discuss how we evaluated our system. Our research question was whether the system can support the design goals listed below. To respond to such question, we conducted an insight-based evaluation with two groups of domain experts, 5 people from industry, from the Austrian Chamber of Commerce, and 2 people from academia. We recorded their interaction with the system and then encoded the insights we could identify by scale and whether they were obtained with or without the support of models. We asked the participants to voice their thoughts as they used the system. The industry participants were interviewed together to accommodate their schedule, while the participants from academia were interviewed separately. Both had roughly the same interview schedule as shown in the slide. These are real examples of insights we gathered during our evaluations, and also this slide shows how we subsequently encoded them. In total, we recorded 56 insights, roughly spread equally over the different scales, with a substantial percentage of insights obtained through models. These two elements suggest that the system could achieve the first two of the design goals. By analyzing the different usage between the two groups of participants, we found that people from industry were more interested in the local effects of policies, with more insights on the regional and local scale, while the people from academia were more focused on financial shocks on larger scale, therefore suggesting that the system could adapt to the workflow of different types of experts. Throughout all this project, we learned a few important lessons, one of which is the potential of 2D plus applications. We found that they provide increased engagement also to experts accustomed to Excel and tabular visualizations. We also found that small guidance elements, and guidance is a very important and hot topic in visual analytics right now, can substantially improve the user experience. Finally, the incorporation of domain knowledge, especially in context of incomplete or uncertain data, is a very welcome feature, while still largely under-investigated. In conclusion, we presented a visual analytics system for the visualization of micro and macro financial data and firm-to-firm transaction networks. The natural evolution of this work would be the integration of a visual tool for the constraint generation and the expansion to multinational financial ecosystems. As this is a CGF invited paper, it is already available and in open access. Follow the links in the slides to get to the paper and to the code repository. Thank you for watching.